In my talk, I'll give a few examples of applications of tau functions to the geometry of modular spaces. The term tau function has different meanings in different areas of mathematics. So the tau functions that I want to discuss in my talk, they originally come from the theory of integrable systems. And they are generating functions for commuting flows. The aim of the talk is to interpret these functions as sections of certain line bundles on modular spaces and to compute their divisors. This computation will provide new relations in the Picard groups of some modular spaces. Well, that's an outline of my talk. Let me add that this is a joint work with Dmitry Korotkin. It's joint. And partly with Alexei Kokotov. So let me give the first example of a tau function. This is the so-called Dubrovin's isomonodromic tau function. This function is well, it appears in an isomonodromic problem that is relevant to Dubrovin's construction of Frobenius manifold structure on the space of meromorphic function on Riemann surfaces. So let me define it carefully. This function lives on the space of meromorphic functions. Let's denote it by H, curly H, tilde, GD. This is the space of triples. A smooth curve of genus G. A canonical symplectic basis in the first homology group of C. And a meromorphic function of degree D on C. So there is a natural equivalence relation. We identify isomorphic triples. And we want to consider only generic meromorphic functions. What does it mean, generic? Generic means that this function considered as a holomorphic map from our curve to the complex projective line has only simple critical values. So let me values. So let me elaborate. So this is a projective line. Let's take a critical point, critical value. We will denote the critical values by zi's. And over this critical point, we have d minus, oh sorry, that's degree d, of course. We have d minus 1 pre-images. D minus 2 of them are regular points, and there is just one point of order 2, one critical point of order 2. So that's the curve C. The number of critical values over generic function can be easily computed. That's 2g plus 2d minus 2. And that's exactly the dimension of this space, H tilde GD. And for the sake of convenience, I'll also denote this number by simply n. So there are n simple critical values, and there are n corresponding critical points that I'm going to denote by xi. And one more important remark is that let me write it on this blackboard. These are the elements of a canonical symplectic basis in the first homology of C. A cycles and B cycles. So let me call it a fact. And this fact is that the critical values are local, are holomorphic local coordinates. On the space of generic meromorphic functions, H tilde GD. Okay, so now I need a couple of additional notions. The first one is the so-called Bergman kernel. Bergman kernel, let's denote it by B of xy, is a bidifferential. It lives on the product C cross C, and it's a one differential with respect to each of variables. It satisfies three properties that characterize it uniquely. So the first property is that that's the differential of the second kind with respect to each of these two variables with quadratic residue 1 or by residue 1. So when x is close to y, this is it behaves like 1 over x minus y squared. This is as y tends to x. Its second property is that it's symmetric. And the third property is that its A periods are all 0. The integrals over A cycles of B of x, y with respect to the first variable are 0. So these three properties characterize this bi-differential uniquely.
And it's holomorphic in x and y.
Yes, away from the diagonal here. The only singularities on the diagonal, the singularities of the second order.
It's not real analytic, it's complex analytic.
Sorry?
I mean, it's complex analytic holomorphic.
Yes, right.
Not real analytic.
No. That's it's complex analytic.
Singularity is out of the diagonal.
Yes. Okay, so let's now look at the asymptotic expansion of this kernel near the diagonal in the product. So we know that the first term is 1 over x minus y squared. Then we have something regular. Let me write it in the form 1 over 6 times SB of x plus something of order x minus y as y tends to x. So here SB of x is the so-called projective connection on C. What does that mean? It means that under the change of coordinate, a local coordinate change, it transforms like a quadratic differential plus an additive term that is just the Schwarzian derivative of the coordinate transition function. So what is the Schwarzian derivative? I'll tell you now. We will also need the Schwarzian derivative of a meromorphic function, and by definition this is the third derivative of f over the first derivative of f minus 3/2 the second derivative of f over the first derivative of f squared. So that's what is called the Schwarzian derivative. And if we take a meromorphic function and consider Schwarzian derivative, this is also a projective connection on C, which is meromorphic. So this is a holomorphic projective connection, and this is a meromorphic projective connection. So when we have two projective connections, we can take difference between them, and then we get just a quadratic differential. So let's subtract SF from SB. As I said, this is a meromorphic quadratic differential. Let's divide it by df. That's a meromorphic abelian differential. So the ratio is a meromorphic 1 differential or abelian differential. So its residues are well defined, and we will be interested in its residues at the critical points. There are n of them, so let's take a residue at each of them. It's a well-defined number. Let's multiply it by 4 for the sake of convenience to make the following formula, the subsequent formulas, simpler. And that's exactly a partial derivative of the logarithm of tau function. So one can consider this as a definition of the tau function.
So f here is like an arbitrary.
F, look, tau depends on triples, okay? The arguments are triples. So
N is the number of critical values of F.
N is the number of critical values, yeah. And the same as that's the same as the dimension of the space.
So it means once you fix a critical point of the function, it's determined.
Well, up to some choice, up to a finite choice. So that's the definition. And an important fact that goes back to Dubrovin is that this differential equation written here has a global holomorphic solution on the space H tilde GD that is nowhere zero. Holomorphic function on H tilde GD. Okay, so now we know what a tau function is, at least in one example, and now we want to play with it a little more. So we want to consider the factor space of the space of meromorphic functions, of generic meromorphic functions, that is close to the modular spaces associated with complex algebraic curves. So now I want to define what a Hurwitz space is. A Hurwitz space is essentially the space of meromorphic functions factorized by some natural group action. So we take, let's denote it by H without tilde, GD, and this is H GD tilde factorized by by a natural group that acts on the space H tilde. So the first of these two groups that act naturally on this space is the symplexic group, the group of integer symplexic matrices of size 2G by 2G. Yes. That's the group that takes one basis into another. So we want to get rid of this restriction. And the other group is just PSL 2C, and that's the group of automorphisms of the projective line. So now we identify functions that differ by a linear fractional transformation. So after factorizing by this group, by this semi-direct product, we get a smooth complex manifold. But now its dimension is 3 less, so its dimension is n minus 3, or 2G plus 2D minus 5.
I'm sorry.
Yes?
You say a semi-direct product?
Yeah, I think so.
How they operate on each other to define the semi-direct product?
Well, because I think that their actions do not commute. I'm not sure, just to be sure. I think they almost commute, but they
would guess they commute, but
well, maybe up to, well, some finite group. Yeah, that's what I think, yeah. Okay, so
is there derivative with respect to zi or xi?
zi, xi are points on C on the curve, and zi's are just complex numbers. Yeah, zi's lives on the projective line, so these are just complex numbers, and xi's are points, and we take residues at points.
No, moduli are complex numbers.
Right.
Projective line. Local moduli.
Okay, so
globally defined function.
yes, I told that. Yeah, it's globally defined, it's holomorphic, and it's nowhere zero.
Zi is a local coordinates.
Local.
Zi is only local.
Yes,
Local coordinates. Okay, so now we want to compactify this space, and there is a natural construction that is called compactification by admissible covers. So the space of admissible covers that's denoted by H bar GD. It of course contains HGD as a Zariski open subset, and this space was introduced by Harris and Mumford. In their work on the quadratic dimension of the modular space of curves. So how does this compactification by admissible covers look like? Admissible covers are covers of nodal curves by nodal curves. So now we allow nodes. We will be interested only in divisors here in the space of admissible covers. So for us it will be sufficient to consider the base consisting of two rational curves intersecting at one point. So that's the rational curve that is the base, and there is a branched cover over it. That is a connected nodal curve, and this projection is a smooth ramified cover away from the nodes. And over each node, there is a node in the cover. And an important property that characterizes admissible covers is that at each pre-image of the node here, the ramification indices for two branches of C that intersect at this point have the same ramification indices. So for both branches, the ramification index at each node is the same. So let's denote these ramification indices by numbers M1 to MR. R is the number of preimages of this node, and of course it's clear that the sum of mi's is just a degree of the cover, and well, so the set of numbers mi is a partition of D. Let's call it mu. that's a partition of D. And let's denote by K and N minus K the numbers of critical values or branch points on these two irreducible components of the rational curve R. On the irreducible components of R. So R consists of two rational curves that intersect at one point, smooth rational curves that intersect at one point. So there are K critical values on one component and then minus K on the other component. So there are N of them together.
So you replace P1 by this curve in the projection there.
Yeah, so
instead of projecting C over P1, project C over such a rational curve.
Yeah, so this P1 degenerates into a reducible curve, and the critical values, they spread between these two components. So K go to one part and N minus K to another part. And so now if we add admissible covers to the space of smooth covers, we will get an algebraic variety. That is called the space of admissible covers. Compact algebraic variety. Which is good, but it's no longer smooth. So just let me now mention a few properties of the space of admissible covers, namely H bar GD. So this space of admissible covers comes with two natural maps. One of them is the branch map that associates a point in the modular space M0n of n-pointed rational curves to a point in the space of admissible covers. The image is just a collection of critical values up to the isomorphism. And there is also a forgetful map pi to the modular space of curves, to the Deligne-Mulford compactification of the modular space of curves. We just forget about the meromorphic function and keep track only of the curve itself. So this space comes with two natural projections. Now, these two spaces are quite good. They are smooth orbifolds, smooth complex orbifolds. This space is even a smooth manifold. Unfortunately, this space is not an orbifold. It's even not normal, but it admits a nice smooth normalization. So we can think of it as a smooth. Its normalization is smooth. It's easy to explain how this space. Okay, just I'll tell that maybe a little later. So,
What about keeping both G and N?
sorry?
What about keeping both genus and the number of mark points? MGA. There is no.
What do you mean?
The critical point upstairs. Keep a critical point upstairs.
Oh,
It could be MGM.
well, there is something, because these two spaces, they have the same dimension, and this space has smaller dimension. So you have some subspaces here. Well, just
You're saying you can do it because the MGN would have higher dimensions than H.
no, it has the same dimension as H.
The same.
Well, that's
H bar has dimension n, but to reduce by the group actions.
yeah, n minus 3, and this space has n minus 3, and this space has dimension 3 G minus 3.
Minus 3 come from factoring through the group.
Yeah, so it depends on the values of G and D and N. Yeah.
So HD, GD is the new Markov type.
H, D, G, D, no, it's not normal even. So let me describe the compactification divisor first, and then I'll tell how this space looks like near these divisors. So the divisors, the compactification divisors are parameterized by actually two sets of data. First by this partition, and second by this number k. So the complement of HGD in HGD bar is a union of divisors. All divisors are understood in the sense of Cartier. Okay, so and these divisors I denote by delta mu k. They are not irreducible, but they are divisors. So, and it's clear that k must be at least 2. Otherwise, the stability condition will not be satisfied. Okay, so how does...
And what is the partition for the generic case? I mean, HGD. It's
well, just
1, 1, 2.
Any.
Okay.
Well, many of them are possible. There are many of them.
For the original space HGD without adding the divisors.
Then there is no mu. They are these are well interior points. Okay, so now let me explain to you how this space looks like near the divisors. In the transversal direction to this divisor, this space looks like a singular curve in CR given by the equations. Well, okay, so let me use coordinates W here. W1 to M1 is equal to W2 to M2, and so on, is equal to WR to MR. And it's easy to see that such a singularity is easy to normalize. So the normalization of this space is smooth. So that's a pretty simple singularity. Okay, so let me continue with the tau function. How to push down the tau function from the space H tilde, from the biggest space to the space of admissible covers. To do that, we just divide it by the van der Monde determinant of the critical values. So let's denote by W of Z1 up to Zn, the usual van der Monde determinant. And the fact is that if we put eta to be tau to the n minus 1 over, over the van der Monde determinant to the 6, then this thing descends to a holomorphic nowhere 0 section of the line bundle of the pullback of the Hodge line bundle, or more precisely to the power of the Hodge line bundle. So let me write it here, and I'll explain what it is in a second. Lambda to the 24 times n minus 1 on the open part, of course, on HGD. So what is the Hodge line bundle? So on MG bar, there is the so-called Hodge bundle, whose fibers are the spaces of holomorphic abelian differentials. Let's take the determinant of this bundle. That is what is called the Hodge line bundle, and it's usually denoted by lambda, and pull it back to the space of admissible covers, and then restrict it to this as a risky open subset. Then this eta, the ratio of two objects, holomorphic objects, is a holomorphic section of this line bundle here. So we know that how to get a section of a line bundle out of eta. Now the next step is to compute its divisor, or in other words, to study its asymptotic behavior near the compactification divisors in the space of admissible covers. And doing that carefully, one gets a non-trivial relation in the space, in the Picard group of the modular space of admissible covers. So let me call it a theorem. It was proven by Kokotov, Korotkin, and myself some time ago, and it says that the Hodge class, let me write it this way, for lambda, understood as an element in the Picard group of the space of admissible covers, H bar GD, in the rational Picard group, one has the following expression for lambda. The Hodge class is the sum over k from 2 to half the number of critical values, the sum over all partitions of the degree okay. here we have the product of ramification indices at the nodes, M1 to MR, times some expression that is symmetric with respect to replacing k by n minus k. So it's k times n minus k over 8 times n minus 1, minus 1 over 12, d minus the sum over I from 1 to r, 1 over mi, times the class of the boundary divisor delta mu k. So that's the formula that we got, and this formula was not known before. It was known only for d equal 2, and then it reduces to a well-known formula by Kornalba and Harris that expresses the Hodge class on the hyperelliptic locus in terms of the boundary divisors. Well, but in this general form it wasn't known.
This is a relation in the Picard group?
Yes, that's a relation in the Picard group.
What is the tau function?
Tau function, well, tau function is here. This is the van der Monde. The ratio is the section of this line bundle. That's where is tau. And the rest is just the divisor of tau. Since it's nowhere zero on the open part, well, its divisor lies on the boundary. And then we look at the asymptotic behavior of this eta near the boundary and compute the order of vanishing. And that gives the coefficients in this formula. Okay. So soon after we published this formula, it was proved by pure algebraic method, algebra geometric methods by van der Heer and Kouvidakis. So they proved this formula using Grothendieck-Riemann-Roch. So they got the same coefficients, so, which is pleasant. And they also applied this formula to answer a long-standing question by Harris and Mumford about the classes of the so-called Hurwitz divisors in the modular space of curves. So these Hurwitz divisors, they are important for computing the codierite dimension of the modular space of curves. So that was one of the tools that Harris and Mumford used. Well, okay, so now I think I still have 15 minutes.
You have...
Yeah, I started at...
You have 15 minutes.
Okay. So let me briefly mention some other examples. So another example, example 2, is about the modular space of abelian differentials. Well, again, we start with a rather big space, HD tilde, that consists of triples C, the canonical homology basis, and a holomorphic abelian differential, say W. And we again assume that it is generic that means that it has only simple zeros. And the number of zeros is well known by ring on the rock. It's 2g minus 2. So what are coordinates here? There are natural coordinates on this space that are called homological coordinates. Some people call them Kontsevich-Zorich coordinates, but they were certainly known before Kontsevich and Zorich. So the coordinates are like that. These are essentially the periods of this differential. So the first g coordinates are a periods. The second g coordinates are b periods. So we have 2g coordinates, and the dimension of this space is 4g minus 3. So we need 2g minus 3 coordinates more. So we consider relative homology. So we just consider the integrals of w from one simple zero to all others. So let's assume that we denote zeros of w by x j. So the last one is x to j minus 2. That's x j, and this is this is z 2g plus g. So we get 4g minus 3 coordinates altogether, as it should be, and these are local coordinates on a tilde.
3g minus 3 moduli for the curve, g parameter for the form. Not 4. You
Sorry?
say 4g minus 3.
Yes, 4g minus 3.
Yeah, 3g minus 3 by anyone for the moduli of the
Yes, and g.
G more parameter for the
Exactly. Yes. Okay, so now we can define a tau function in a way similar to the case of meromorphic functions. Since in the definition we only use the derivatives of f and not f itself. So by definition, d log tau, del log tau over del zi, where zi's are homological coordinates, is minus 2 over pi times square root of minus 1. Integral over si. That's what is si? I'll explain in a second. And here we have the same expression, the Schwarzian derivative of the projective connection minus SW over W. So now SW is the second derivative of W over W minus 3/2 of W prime over W squared. And what are SIs? So the first G of them are just minus BI's. The next G of them are AI's. And let me recall that there are two G minus 3 paths from xj to x2g minus 2, from simple zeros to the last zero, sort of, and as j plus 2g is just a small circle around xj, the jth zero. Okay, so, and again, as in the case of meromorphic function, this tau extends as a holomorphic, nowhere vanishing function on the space A tilde. So then we play the same game. We factorize A tilde by a natural group.
In this case, tau has no relation with isometer on A.
No, nothing I know about.
Számolzott tau, számolzott.
Actually, we can focus understanding from one
Omega W was 1/4.
right?
Right.
And then you write S of W.
Yes, that's a projective connection, and that's a projective connection.
1/4. How do I calculate?
Right,
W has to be a function in order.
It's not a function, it's a projective connection. And this is a projective connection. This difference is a quadratic differential. And you divide it by
choose a local
1.
coordinate, choose a
So I have to choose a local coordinate for
and then
W.
it's independent.
This Schwarzschild applies to the primitive also.
Yeah.
Because Schwarzschild I apply to function, not to one.
The primitive, the integral of the
Right.
Okay, so first we factorize A tilde by the symplectic group over the integers times C star. C star acts on W by multiplication.
Schwarzschild derivative of the primitive.
Okay, and there is a simple compactification of this space, A bar G, which is just the projectivization of the push forward, or direct image of the relative dualizing sheaf. So let me recall what the relative dualizing sheaf is. That's a sheaf, well, on the universal curve. Along fibers, this is just along each fiber of the universal curve. This is a cotangent bundle to the curve, or the canonical bundle to the curve. It's a dualizing sheaf on each fiber of the universal curve. And we denote this map by pi. Then here we have the push forward. That is a G-dimensional bundle on mg bar. It's better to say sheaf, but yeah, it's if to understand it properly, one can call it a vector bundle. Anyway, this thing, this thing is well defined, and the complement. So if we subtract AG from here, we'll get some number of divisors. So some of them are inverse images of the boundary divisors of mg bar, and there is also a divisor that we call delta deg, the divisor of differentials with non-simple zeros, plus delta naught, delta naught is the pullback of the divisor of irreducible nodal curves here in mg bar, plus delta 1 plus and so forth up to delta integer part of g over 2. So these are just all these are pullbacks of the corresponding divisors in mg bar. And there are, well, we can take their classes in the Picard group, of course. So and there are another two classes that are of interest to us. They are the Hodge class, lambda, that I already mentioned. That's, well, that's the pullback of the Hodge class on mg bar. And there is the tautological class that I denote by psi. And that's the tautological class of the line bundle associated to the C star action. Okay, so these are the divisor classes, but there are too many of them. The dimension is the dimension of the rational Picard group is by 1 less than the number of these divisors, and there is non-trivial relation that I want to write down. Let me call it a theorem that was proven by Korotkin and myself, and this theorem gives the following expression for the Hodge class in terms of the other classes. So the Hodge class is g minus 1 over 4 times psi plus 1 over 24 times the class of the divisor of degenerate differentials with non-simple zeros, plus 1 over 12 the class of the divisor of irreducible, the pullback of the divisor of irreducible curve, plus 1 over 8, the sum over j from 1 to the integer part of j over 2, the classes of the divisors delta j. So this formula was also proven by other people by different methods, and it appeared to be useful in understanding better understanding Kontsevich-Zorich conjecture about the rationality of the sum of Lyapunov exponents of the Teichmüller flow. So what are other applications? We also wrote analogs of this formula with Korotkin for the case of quadratic differentials, for the modular space of quadratic differentials. And quite recently, Mikhail Basok a student, an undergraduate student actually, at the Chebyshev laboratory, he applied this technique to the modular space of odd spin structures on algebraic curves of genus G, and got an analytic proof of a well-known result of Gavril Farkas. And well, this work is very promising because Farkas was able to prove only part of what he wanted to do. And maybe this approach will give the missing parts of what Farkas wanted to do. He needed that for studying, well, the codary dimension of this space. Or, well, in other words, for birational classification of the modular space of odd spin structures. Okay, that's all that I wanted to say. Thank you for your attention.
Questions, please?
So wasn't this conjecture by Kontsevich and Dorsch proven by Viana and Avila?
If you take the Hodge bundle on the modular space, there is a natural action of GL2R group, and there is a flow. So for this flow, there are the so-called Lyapunov exponents. The conjecture is that the sum of this Lyapunov exponents is a rational number. Yeah, Kontsevich and Zorich wrote this number as a ratio of two intersection numbers, which involve lambda, psi, and the one mysterious class. So these are, well, the ratio of the form, well, just mysterious class sigma with lambda over, say, this class sigma with psi. So these two classes, they are of course well known, but this class is kind of, but that's the class of the foliation. It's not known whether this class is any good. If it was a rational class, then the conjecture would be established. So we split this sigma into two parts, and one part, about one part we could tell that it's rational, and the other part, well, it also has some meaning in the theory of dynamical systems. And that's, well, it's something like Veitch constant, yeah, I think that's the right name for it. So we didn't prove it, but
Then Avila and Viana did some work. Avila and Viana did some work about this Veitch constant.
yeah.
Good example.